So this video is for slides 7 through 19. I'm going to go into a little more detail here. The confidence level could be 90 or 95 or 99% or any other percentage really. So a 95% confidence level means that if we constructed 100 intervals, 95 of them would contain the parameter mu or p that we are estimating. It's like we're trying to pin down something that's unknown and place a boundary or an interval around it. The next slide shows 68%, 95%, and 99.7% confidence intervals and whether or not they capture the parameter. Now, a 68% confidence level isn't super useful, but these are the percentages from the empirical rule, so that's where you've seen those particular percentages before. So this is from maybe our textbook or from another textbook, I can't really remember, but I took a picture of the page. Basically, mu is what we're trying to estimate, and the green lines, which I kind of want to zoom in on, the green lines are our attempts to create an interval, and sometimes we do a really terrible job and we completely miss the population parameter. So there would be an interval where we missed, there's another one where we missed. Here our intervals missed the population parameter mu, but a lot of the time the interval that we created contains the population interval mu. Again, there's another epic fail. Epic fail. You created an interval from something to something, and it didn't actually end up containing the elusive and mysterious mu of the population. Now, this was 68%, so that's why there's a lot of fails. A 95% confidence level means that you are only going to miss 5 out of 100 times. There's a miss right there. 2, 3. Do you see any other misses? I think I see some misses right here. Those intervals missed mu. But most of the time, our intervals capture mu. And then 99%, oh, those are actually 99.7% confidence level. So we've boosted our confidence level a lot higher, and notice that these intervals are wider as well, like I said before. They're wider, and all of them captured mu. So the problem is that we have wider intervals, which is less information. It's like saying, I am pretty confident that my student ages are between age 18 and age 95. I can cast a wide net, and then I'll be more likely to capture mu. So as the confidence level increases, the confidence intervals get wider. Can we ever have 100% confidence? No. What is the downside to using 99.99 confidence interval? Well, you'd have a super wide interval. And sometimes a really wide interval is not that helpful, not that informative. So you want to find a balance between certainty and too wide of an interval. I feel like 95% is kind of a sweet spot. Really, this comes back to what we learned in chapter 7 about the distribution of the sample means. We know how much variability in the sample mean there is. Let me repeat that. We know how much variability there is in the sample mean. We know how much they can fluctuate from the population mean, because in chapter 7 we developed this formula. The standard deviation of x bar is the standard deviation from the underlying population, sigma x, divided by root n. So that tells us how much variation there is in X bar. 68% of the sample means will be within 1 standard deviation of the population mean. 95% will be within 2 standard deviations, and by standard deviation we are referring to this quantity. So the empirical rule is helpful here. And remember that when we say within 1 standard deviation, we're saying z equals 1. Here we're saying z equals 2. Here we're saying z equals 3. Okay, now that's... All right, so the 95% confidence interval is x bar minus z, but here z is 2. So x bar minus z sigma over root n, that is our EBM. And again, x bar plus the EBM. So 2 is the z-score for our confidence level. And EBM is z sigma over root n. So you're going to want to have all of these important reminders on your notes sheet. And I know you're going to copy them from your notes worksheet that you're doing this week onto your notes sheet for the test. Here is just a little sketch of z-scores and the probability of x bar landing between -2 and +2 is 95%. And I actually lied. It isn't 2, it's -1.96 and +1.96. So as we get a little bit more precise, 2 was sort of a ballpark number, and actually the z-scores that we're looking for are plus or minus 1.96. For the confidence level of 0.95. And I think you have that in that little table on your notes sheet on page 1. And we can confirm that. So I'm going to use my calculator to confirm second distribution, normal CDF. I'm just trying to confirm that there's 95% area between these two boundary values. So normal CDF, I put in the lower bound, the upper bound, and then that's mu, and that's sigma. Remember the standard normal distribution, the z-scores have a mean of 0 and a standard deviation of 1. So that's why I'm putting in 0 and 1 for mu and sigma. So -1.96, enter. Positive 1.96, enter. Mu is 0, sigma is 1, enter, enter, and there it is, 0.95%. So I honestly would be good with that. Here I'm just explaining that there's alpha, which is 1 minus the confidence level, and that is 0.05. This is the area in both tails of the normal distribution. So 0.05 is the area outside of what we're talking about, and so we split that in half. So alpha over 2 is 0.025, and that's the area in each tail. So there it is, area in each tail, 2.5%. And then we find the z-score. And let's see, do I do that on the next slide? How did you get 1.96? Yeah, so this is where I explain where that came from. Z alpha over 2 is just, how do you find the boundary that will perfectly hold 95% of the x bar values? Find the z-score that puts the confidence level in the middle of normal 0, 1. So the z-score has an area of 1 minus alpha over 2. So that's 1 minus 0.05 over 2. So that's 1 minus 0.025, which is 0.975. If we do inverse normal, 0.975, we will get 1.96. So I'll walk you through that. Second distribution, inverse normal, 0.975, 0 and 1. The 0.975 is the area to the left. So we're saying what z-score has 0.975 area to the left of it. Enter, enter, and there's our 1.96 z-score. Now the TI-84 Plus has the option to actually make this a little less complicated. If we just put 0.95 and say that that's the area in the center, then we'll get the exact same result. So we didn't have to go through this whole contortion here. Oh, interesting. It gives us both z-scores, the negative 1.96 and the positive 1.96. But I think the TI-83 and some of the older TI-84s don't have the option to choose left or center there. Anyway, finding z alpha over 2 is complicated, so just use the table. You might want to just erase from your brain a bunch of the stuff I just said. It's almost too much information. Really, what I was showing you is how do you go from 95% confidence level to 1.96 z-score. So I showed you the process, but you are welcome to just keep this table on your notes sheet and reference it as we go. I'm showing you the why, but you don't need to know this. And let me see what slide I want to stop at here. I'm going to go to slide 19. Okay, so we're almost there. Let's just go a little further. I think this is just reiterating everything I just said. This is just another picture showing the sample mean here, and then x bar plus EBM, x bar minus EBM. There's that formula again. Makes it pretty easy. As I'm teaching this, I'm just feeling like, yeah, this is no big deal. In the problem, you will be given x bar and confidence level and sigma, and then you will find z alpha over 2, and you might prefer to just find it from the table. I did provide a link to you, because what if we give you a really weird confidence level? What if we said 93% confidence? And then you might panic because that's not on your table. Your table only provided 90, 95, 98, 99. Well, I provided a link to a website that can give you the z-score for any confidence level, or you can go through this process as well. For this one, alpha would be 0.07, alpha over 2 would be 0.035, and then you would do 1 minus that, so that would be inverse normal of 0.965, 0, 1, and then boom, you'd have your z-score. So it's a little annoying and convoluted, but not too bad. Once you have your z-score, then you go through the EBM, z times sigma over root n, no big deal. And then you do x bar plus or minus your EBM, and then you make your interpretation of it. And this is something that I said before, so again, increasing the confidence level increases the error bound and the confidence interval gets wider. So there's a 90% confidence interval and there's a 95% confidence interval. And again, there's an overview of what we're covering in Chapter 8.